Hello everyone, this is Yo from class EL6303. In this video, I will solve question 1 in homework 10. For this question, we are asked to collect the definitions and simple properties of examples of stochastic processes from Professor Chen's lecture notes. For the first process we need to look at is Poisson process. It's defined like this: between the interval between t1 and t2, the probability of n t1 and t2 equals to k equals to e to the power of minus lambda times t times lambda times t to the power of k divided by k factorial. We got two properties for this process. The first property is the intervals T1 and T2 and T3 and T4 are non-overlapping. We can get the n T1 and T2 and n T3 and T4 are independent. The second property we get is at a time moment t, there is no more than one Poisson point. Using the point ti, we form the stochastic process x of t equals to n0t. So the first order probability method of this process is equals to the probability of x of t equals to k equals to e to the power of minus lambda times t times lambda times t to the power of k divided by k factorial. The mean of a Poisson process equals to lambda times t. The autocorrelation of a Poisson process equals to the lambda squared times t1, t2 plus lambda, the minimum value of t1 and t2. The autocovariance of a Poisson process equals to the lambda squared times t1, t2 plus lambda minimum value t1 and t2 minus lambda times t1 times lambda times t2 equals to lambda minimum value between t1 and t2. The second process we need to look at is Poisson increment process. It's defined like this. It's y of t equals to x of t plus epsilon minus x of t divided by epsilon. The first order probability method of the Poisson increment process equals to the probability of y of t equals to n over epsilon equals to e to the power of minus lambda times epsilon times lambda times epsilon to the power of n divided by n factorial. The mean of this process equals to the lambda. And the autocorrelation of this process we need to discuss in two conditions. The first condition is when t1 minus t2, the absolute value of this is greater or equals to the epsilon, and the autocorrelation is equals to the lambda squared. Otherwise, if the minus t1 minus t2, the absolute value of there is less than epsilon, then the rt1 t2 equals to the lambda squared plus lambda over epsilon minus lambda times the absolute value of t1 minus t2 over epsilon squared. Now let's look at the outer covariance of Poisson increment process. The CT1, T2 also discussed into these two conditions. If the absolute value of T1 minus T2 is greater or equal to the epsilon, is equal to the 0, otherwise is equal to the lambda over epsilon minus lambda times T1 minus T2, the absolute value of them, and over epsilon squared. And for the point impulse process, it's defined like this. Z of t equals to conduct the derivative of x of t with respect of t. Here, x of t is a Poisson process. And the mean of point in post-process equals to the lambda. Autocorrelation of it equals to lambda squared plus lambda times dirt T1 minus T2, and the outer covariance of it equals to the lambda times dirt T1 minus T2, and for the fourth process is semi-random telegraph signal. X of t is defined based on the Poisson points. The number n T1, T2 of the points Ti in the interval T1 and T2 of length t equals to T2 minus T1 is a Poisson random variance with parameter lambda times t. The probability of n T1, T2 equals to k equals to e to the power of minus lambda times t times lambda times t to the power of k divided by k factorial. Here we define x of t. When x of t equals to 1, that means k is even in the interval between 0 to t, otherwise it equals to the minus 1. So the first order probability method of this process is the probability of x of t equals to 1 equals to the e to the power of minus lambda t times e to the power of lambda t plus e to the power of minus lambda times t divided by 2, and the probability of x of t equals to the minus 1 should equals to the e to the power of minus lambda of t times e to the power of lambda of t minus e to the power of minus lambda times t divided by 2. Now let's look at the mean of this semi-random telegraph signal. The mean is equals to the e to the power of minus 2 times lambda times t, and the autocorrelation of it should equals to RT1 T2 equals to e to the power of minus 2 times lambda times the absolute value of T1 minus T2, and its outer covariance equals to the e to the power of minus 2 lambda times T1 minus T2 absolute value of it minus e to the power of minus 2 times lambda times T1 times T2. And the fifth process, we need to look at the random telegraph signal. Here is a y of t equals to the a times x of t, and the probability of a equals to 1 equals to the probability of a equals to minus 1. Both of them got the probability is a half, where x of t is a semi-random telegraph signal. The first order probability method of a random telegraph signal process is the probability of y of t equals to 1 equals to the probability of y of t equals to the minus 1 is a half, and the mean of this process is 0. The outer correlation of T1 and T2 equals to e to the power of minus 2 lambda times the absolute value of T1 minus T2, and the outer covariance is equals to the same as the outer correlation of it. So the sixth process, we need to look at the random walk. If we toss a fire coin n times, k is the number of highs in n toys. X of n times t equals to k times ice minus n minus k times ice, and is equals to 2k minus n times ice. The first order probability method of it should equals to the probability of x of t equals to x of n times capital T equals to Ris, and is equals to c n plus r over 2 1 over 2 to the power of n for t is greater than n times capital T and is less than n plus 1 times capital T. And the mean of this process is 0. The autocorrelation of this process is equals to the minimum value of n and m times s squared. And its autocovariance is equals to the minimum value of n and m times s squared. It's just the same as its autocorrelation. And for the last process we need to look at is a Wiener process. It's defined like this: W of t equals to the limitation of x of t when capital T is closing to 0, s squared over capital T is closing to alpha, and n is approaching to infinity. Here x is the random walk, so the first order density function of f w of t equals to 1 over 2 pi times alpha times t square root of it, and times the e to the power of minus w squared over 2 times alpha times t, and the mean of a Wiener process is 0. The autocorrelation and the autocovariance, they are the same. It's the minimum of T1 and T2 times alpha. So this is the answer for the question 1. Thank you.